Okay, so now we're just going to jump into the part where we do repeated linear, and then we'll end with irreducible quadratics. So that should cover everything. The process for repeated linear is the same or analogous to the process for repeated quadratics. So I will leave that to the reader. Okay, so in this example, you can see that our denominator contains 2 copies of the 2x minus 1. So if I were to write this up, this is really saying 2x minus 1 times 2x minus 1 times x minus 1. So that's what they mean by repeated linear factors. So this guy and this guy are both repeated and they're both linear. So whenever you have that, you're going to have to kind of write both versions of that down. And this is what I mean by that. This is going to equal the integral of a over 2x minus 1. And then because the linear term, the linear factor is repeated, it gets another appearance, except in this case, it will be squared to match up to the power, right? So let's say this was cubed. Just imagine, if you will, for a second, if that had been cubed, I would have yet another one, and then it would be cubed. And that would be a long, boring problem. Okay, but that's not the case, yay. So I took care of my repeated linear factors, and then I still need to remember x minus 1. So now it just remains to go through and figure out what a, b, and c are. Same process as before. In this case, you're going to see that we don't have all the killer x's that we need. And actually, all right, put a pause on that. So I've got x minus 2 over 2x minus 1 squared by x minus 1. And this is meant to equal, yes, I intentionally left the space there. And I know I demonstrated this principle in the earlier video, but the idea again is to just multiply by the whole denominator. So 2x minus 1 squared by x minus 1, and then the same over here. So the cancellation works a little bit differently in this case. On the left-hand side, it's very straightforward. I just get x minus 2, which is fantastic. On the right-hand side, the denominator for a, it only kills 1 copy of the repeated factor, and then the red-headed stepchild survives. So I get a 2x minus 1 by x minus 1. And b, its denominator kills both copies of the repeated linear term. So I only get b by x minus 1. And then for c, that's pretty straightforward. I get 2x minus 1 squared. So you can definitely, I still want to do this both ways. That is comparing coefficients and using the killer x method, because there are times when the killer x is just like, it's so fast, very easy, especially when you have non-repeating linear terms. We're going to see an example after this one where comparing coefficients, like, it could not be faster. So it's good to know both. All right, so let's, so we'll have our killer x and then plus a sidekick. That'd be a great band name. And then here we'll compare coefficients. So I get I'll just take it from the top. So the killer x for us is going to be 1. So if x equals 1, we're going to get 1 minus 2, which is negative 1. Then a, 2 minus 1 is 1. 1 minus 1 is 0. Plus b by 0 plus c times 1 squared. So we know that negative 1 equals c, which is pretty convenient. Our next killer our next killer x is 1/2. So if x equals 1/2, then I get 1/2 minus 2, which is negative 3/2. I get a by 0 times negative 1/2, okay, whatever. And then I get plus b times negative 1/2 plus c times 0 squared. So in this instance, I get negative 3/2 equals negative 1/2, 1/2 b, so that b has to equal 3. So far I'm at c equals negative 1 and b equals 3. So I'm out of killer x's though. So I use my most useful sidekick, I guess, which is just 0. So if I plug in 0, then I get, what do I get? I get negative 2 equals a times negative 1 times negative 1 plus b times negative 1 plus c times negative 1 squared. So, and I know what b and c are. So negative 2, this is just positive a. B was 3, so this is just minus 3. And then c was negative 1, so this is minus 1 because that negative 1 is squared. Okay, fine. So a minus 4 at 4, 2 equals a. So that wasn't so bad. They're not all that nice. Let's look at comparing coefficients. Usually when we have a repeated linear term, it gets a little bit more complicated. And I know some of us could probably benefit from practicing expanding products of polynomials. I say that with love. I noticed some stuff. No shame, just gotta practice it. Okay. So I get x minus, I'm gonna do 0x squared again, just because that helps me visualize how my coefficients match up. So the first thing I'm gonna do is I'm just gonna expand my polynomials. So I get 2x squared. So 2x squared minus 2x minus x plus 1. And then for b, I just get I'm organizing it a little bit differently. Oh boy. Oh no, I can do this. All right, get it together, Walker. So for c, I have 4x squared minus 4x plus 1. So this is another way where I can kind of just look at coefficients without rewriting everything. So I just, my x squareds, I get 2a and 4c. There's so many ways that you can organize your thoughts and organize your polynomials. So this is just another way that you could try to visualize it. It's totally up to you how you do this. And it's totally okay to not do the comparison of coefficients method, by the way. You can always stick with the killer plus the sidekicks. So my next guy is I get my linear term, so that's negative 2a B and minus 4C. Okay, so that's 1 equals negative 2A plus B minus 4C. And then for the last, oh, see, look, yep, made a mistake. What was my mistake? My mistake is that I forgot about this guy. So it's negative 3A. Okay. And then for my constants, I get just 1A minus B plus C. A minus B plus B. Negative 2. And so if I throw that into an augmented matrix, I'm going to have 0, negative 2, 2, 0, 4, minus 3, 4, 1, 1. Okay. So let me throw that into my favorite electronic item in the house, which is my TI-83 Plus. This is a 3x4 matrix. Okay, so now I'm row reducing it. Well, I'm making my calculator row reduce it. And by some small miracle, I did not make an error. So when I row reduce it, I get this as the result. 2, 3, negative 1. So this tells me that A is 2, which we got, nice, that B is 3, which we also got, and then that C is negative 1. So this is awesome. Cool, so that's really, again, this is the hardish part for this problem. I guess it's maybe challenging because we've never done it before. The thing that we're about to do next is, I wouldn't say it's easy, but we've done it. So the thing we're going to do next is we're going to integrate. Let me pull our form. So what happens is that this becomes, well, what's really going to happen is that these need to go away. So now we can just replace our A, B, and C. So we said that A was 2, B was 3, and C was negative 1. So this is ln 2x minus 1. For the squared guy, you want to, the idea is just to make a U sub. Like essentially in the first guy actually too, you're making a little bit of a U sub, but I understand if you can do that in your head. For the second guy, it's the same thing. You just want to make a U sub, but again, you can totally do that in your head. So you should get right. So that should be your final answer for the integration. So we only have one more thing to cover, which is what to do when we have irreducible quadratics. So when we have quadratics, irreducible quadratics, what happens is that our numerator becomes a linear term. So just FYI, this is the pattern. What's the degree of a linear? It's 2. What's the degree of a constant? Just kidding. What's the degree of a linear? It's 1. What's the degree of a constant? 0. So we see that when we do this partial fraction decomposition, it always breaks down to where the numerator is 1 degree less than the denominator. I'm generalizing. Of course, when we have these repeated roots, right, that doesn't really apply. But I'm just talking about the factor itself before it's repeated. Similarly, it's 2 to 1, right? So it kind of makes sense for us that if we have an irreducible quadratic, the numerator should be a linear instead of a constant. Again, not including repeated. So for this guy, I've got a cubic. I know I can reduce that a little bit. So I'm going to get 2x minus 3 over x times x squared plus 1. So in the beginning of the first video, I said, hey, x squared plus 1 is an irreducible quadratic. Its roots are complex conjugate pairs. And since this is not a complex analysis class, we're going to just consider this as a irreducible quadratic that exists in the real numbers. What? I'm just trying to say that we're not going to factor it anymore. Okay. So the cool thing about this is it becomes something over x plus something over x squared plus 1 dx. Right, so when we have a linear term, we know it just gets the constant. I just talked about that. For the irreducible quadratic, it's going to look like something else. It's going to be bx plus c. Now, in the textbook, they write the quadratic first. So they have ax plus b, and then they have c over x. It does not matter. It only matters that whatever I say is a, it goes over x. And whatever I say is b and c, that goes with my quadratic. All right, so let's get to it. So we've got 2x minus 3 over x by x squared plus 1, everyone's favorite irreducible quadratic. So this ends up becoming, just by clearing out the denominator, I just get 2x minus 3 equals a by x squared plus 1 plus bx plus c times x. So we're going to do this 2 ways again, because in this instance, the comparison of coefficients is like, if you blink, you'll miss it. It's so quick and easy. So let's do it the hard way first. So 2x minus 3 equaling a by x squared plus 1 plus bx plus c by x. So for sure, x equals 0 is a killer x. Great choice. It's actually the only one. So if x equals 0, then I get negative 3 equals a times 1, which is really just saying a equals negative 3, which is great. And I don't have any other killer x's, so I'm just going to choose another super convenient x value. It does not matter. So, well, we can do 1 and negative 1. So if x equals 1, then I'm going to get negative 1 equals a times 2 plus, So if x is 1, then it's just b plus c times 1. So just plus b plus c. Okay, and now I'm like already annoyed by this because now I have to go plug back in a. So -1 equals -6 plus b plus c. So then I get 5 equals b plus c. And it's not terrible, but it's not great. So we'll do another one if x equals -1. If you're wondering why I stopped at 5 equals b plus c, is because like I have to, because I don't have anything else to do. So if x equals -1, -5 equals a by 2 minus b plus c, make that negative, plus b minus c. And again, a is still -3, so I get -5 equals -6 plus b minus c, so that 1 equals b minus c. And so now I have this system of 2 equations and 2 unknowns. So what I do is I just add them together. I guess I should show this. So 5 equals b plus c, 1 equals b minus c. If I add them, I get 6 equals 2b, so that 3 equals b, which would then imply if b is 3, then c ought to be 2. I don't know, it's not great. I mean, I still loved it because it's math and I love math, but definitely not my favorite. It's not like a trig sub, you know, it's not like good times like that. Let's try the coefficient comparison. So I get 2x minus 3. I'm going to extend this out a little bit. So it's ax squared plus a plus bx squared plus cx. So then I get 0x squared, right? Just again, writing the 0 for my own edification and organization, plus 2x minus 3. And then all my squared, so it's a plus b. And then my linear terms, I have c. And then for my constant terms, I have just a. Okay, cool. So this is already great because I can already see right off the bat by looking at it, c is 2, a is -3, done. All right, so I get 0 equals a plus b. I get 2 equals c. And I get -3 equals a. I mean, I don't know what more I can say to convince you that this method is superior in this instance. So if a plus b is 0 and a is -3, then we know that b has to be +3. You could also throw it into an augmented matrix if you really want to, but I think that's a bit overkill in this instance. Here's what it would look like. What would it look like? Cool. So now we're ready to integrate. I'm going to grab our original expression here, and then I'm just going to kind of fill in a, b, and c. So copy that. So we said that a was -3, so this is the integral of -3 over x, and then b was +3. C was 2, so 3x plus 2 over x squared plus 1 dx. So -3 over x, that's really straightforward. That's just -3 ln x. But 3x plus 2, at first glance, you're just like, oh man, great for a u sub, like because derivative of x squared plus 1, that's going to be 2x. And then you're like, oh, but that little plus 2 is really giving me grief. So this is my recommendation. Split this all the way up. The first and the last, I already know how to do those. Natural log, arctangent. You're supposed to know that. Hopefully you know that. So the middle guy is a u sub, but you already know how to do that too. But let's walk through it. So if you let u be, just kidding, if you let u be x squared plus 1, then 1/2 du is x dx. So what you'll end up with is that the center integral is going to be 3/2 du over u. So I'm going to get negative 3 ln x plus 3/2 the natural log of u. So u is x squared plus 1. And then this is 2 arctan x squared, just kidding, 2 arctan x plus c. That's it. Good luck. You know where to find me if you have any questions.